And let's start from the hard question. Where does C++ run? Yes. That's absolutely correct. Next hard question. Have you seen one? Right, so the word is that the abstract C machine, yes, that's something that's everywhere, but nobody has seen, and it's said that it's even more rare than a spherical cow in a vacuum. But that's an illustration. You can actually see a spherical cow in a vacuum here, but what about that mysterious abstract machine? In fact, C++ runs on the underlying hardware platform. Right? So what the compiler does eventually gets translated into what the machine can understand. What's a machine? In a very simple forms, that's an intermix of two components, memory and compute, interconnected by something. Well, there's I/O, input-output component, which interacts with the rest of the world. We don't care about that for our discussion and leave that aside. Looking a little bit from a historical perspective, at some point of time, processor looked like that. Then gradually it transformed itself into this one. Oh, sorry, we're in Germany, so we need to fix that. Anyone remembers the U880 here? Karl Marx had something good to do to the community, apparently. Right? Then memory initially looked as an array of inductors, coils, basically, storing the magnetic charge. With time that migrated into capacitors, and that got interconnected. So that's where those components are. If we look today at the contemporary platforms, pretty much everything is the same, just they are slightly larger and having a few more pins overall. And the capacity has increased a little bit by a few orders of magnitude. And again, we are not talking about interconnect here. That's quite complex and outside of scope. Let's start from the memory component. So in essence, the contemporary memory system is just an array of capacitors. The element that stores the actual information quantity is a capacitor. The process, it's very simple. The capacitor is charged to some level, you connect it to a sense amplifier, and depending on the direction of the current flow, you can decode that as it's storing a logical 0 or logical 1. That's a destructive operation, therefore you need to revert it back to what it was. Also, you cannot play around the laws of physics. There are leakage currents and all sorts of other restrictions. You cannot hold that information there for a long period of time. If you look from the perspective of the actual use of the memory array, you have an interface into that and you have timing parameters. So let's see how that works. You send out a command to a memory array asking to basically connect a fragment of that array for further processing. Suppose that takes a hypothetical nanosecond. Then the magic happens over there. Basically, you need to connect the fragment of the array. You need to prepare some internal machinery. You wait. And then you send out another address of the component, and then you wait again. And only after that, your data actually can be transferred, read or write, depending on what you want to do with that. And after you are done with this, because of that precise nature of the loss of the charge by the reading or by time, you need to precharge it to return back to the previous stable state. And you wait again. Where's the problem here? If we look into the timing, the actual goodput, or the time spent doing something useful, actually transferring the data back and forth, doesn't look very optimistic on the whole time scale of the memory interface. It's something on the order of 10%. However, that's just a hard reality. And if you look into the marketing documentation, many vendors will claim that, oh, our memory is, well, next generation is way faster than the previous one. What is in fact faster is the actual rate at which you can transfer the data. Generally, memory generation to generation doesn't get noticeably faster. In some instances, it actually gets slower. For a very simple reason. You cannot charge or discharge a capacitor faster than basically the physical restrictions allow for you to do that. If you increase the size of the array, you need additional time to be able to connect those fragments of the array. What in fact increases is the actual rate that you can transfer via the memory module. What shall we do about that? In fact, the reason why you can gain some benefit out of this is by running multiple operations in parallel in your memory. So from an addressing perspective, address is separated in separate components due to electrical signaling reasons mostly. And then you can have operations with that one open page, this small dot at the lower left corner. If you want to if you want to do something else with a different address location, different memory locations, you need to close that particular cell, open a new one, and repeat. That's definitely not optimal. The response to that is banking. So that whole picture is scaled down to a small square here. That's a bank. We can have multiple of those. And one bank can be open for an operation. That means that you can interleave requests into memory, and then you will get some additional actual good put that will be able to use the available memory interface more optimally. Going historically, initially it was thought that 4 banks will be enough, similar to some other quantities that might be enough. Apparently that was not, therefore there's another hierarchy, and we can continue. It's just an additional level of addressing. Then yet again we have some other logical quantities that allow for us to have, in this particular instance, 16 or 32 open pages of memory. And if we look at the contemporary developments, it is increasing. So therefore, if you're optimizing for the memory performance, the important aspect is to have memory requests spread. And we will talk a little bit about the actual mappings in a moment. It is important to have the memory operations spread and not condensed. That might sound a little bit counterintuitive related to caching, and in fact it is, and it's a fine art of balancing the actual caching and what operates on a software visible page size and how that maps on the underlying platform on the actual hardware memory page sizes. Some random topics about new developments in memory systems. There's a trend about HBM, high bandwidth memory. And marketeers might say that, you know, we have a wide interface over there, therefore your actual throughput is way higher. In theory and in paper. In reality, that's not. It's in fact 8 parallel channels. That means that you need to send 8 parallel commands in order to use that. That certainly works fine for the GPUs or for some other parallel platforms. Those inherently can send out parallel requests to different addresses. However, if you are dealing with a sequential scalar code, that is of no major help for you. We're also seeing a major trend of having disaggregated memory. That means from a logical perspective, that's one addressable space, but from a physical perspective, the memory doesn't live locally to the actual compute node. This started with sockets, right? So you have local socket memory and remote socket memory, and that is going further, where you have an interconnect between the actual processor sockets, and the memory is reachable remotely. The question is at what cost? The important part is to ensure the actual coherency, that the cached data in the whole system is seen coherently from any observation point. That is technically that's doable, however, that's expensive. And therefore, if we are looking at the total memory system performance, as a rule, that does not grow that much. We're also seeing proliferation of different memory types like non-volatile memory. Those have similar protocol but very different timing parameters. For example, if you are optimizing your application to run on dynamic memory, and if that eventually gets migrated to a non-volatile type of the memory storage, the performance might be very different, and that might come out as a nasty surprise. How can you influence that, and why is it all important? We all know that the page size is 4 kilobytes from a software perspective. Why shall we care? That's correct, it's 4 or some other quantity. However, that gets mapped into the underlying memory system, and that mapping, first thing, you don't have much influence over that. That happens typically at the boot of a platform, and that's controlled by the low-level firmware there. The second important aspect, you generally don't have influence into that unless you build your own custom platform. Therefore, the best that you can do is to discover that and adjust from the software perspective. So here you see just an extract from the DDR4 specification. It's the same capacity memory module, but it may come in different physical organization. And the logical page size is 4 kilobytes. However, the physical might be half a kilobyte, 1 or 2. And the mapping, how the address gets translated, whether that's module rank, bank group, bank, or some other grouping, that depends on the platform specifics. Therefore, if you care about the performance to the last percent, this is an important aspect to be aware of, and to a level be ready to adjust to that. What you can gain in the practical terms, a few percent of performance difference is rather easily achievable if you rearrange your data structures to be aligned with the physical and not logical memory page size. Summarizing why and how memory is important to that. So memory is, in fact, is a client to the compute core. Can be local. Today, generally, all the memory is a remote. Of course, even if you have one single socket, from a perspective of the path that goes from the compute core into the memory system, it's quite complex and frequently very nonlinear. If you can avoid having remote physical sockets, please do. It's way more practical for increasing the performance is to reduce the number of sockets and not to increase. The coherency synchronization protocols are really expensive. Therefore, it's more practical to go with a single socket having, say, more cores if you are core bound than having a platform that has more sockets and less processing cores. Again, that's not necessarily always feasible. That depends on the actual task at hand that you need to have. It might be that you are limited by the actual single thread performance, and therefore you have to have less number of cores. Yes.
Just to understand, socket is a thread or is it a line, like a memory line?
If you could please wait for the microphone. Well, I will restate this one. So the question was about what's a socket, whether that's a thread or a core, something like that. No, that's on a lower level below. Socket is something that you can take in your hand that has pins or pads and goes into the other part of the connection. So what I was showing here a few pages ago, right, well, a few tens of that's the socket here on the left side, right? So this one, right, so basically a physical package, right? Same thing as here, right, that's the memory socket. It's a physical quantity, right, and threads, cores, and whatnot, they are already logical abstractions which live way high above the food chain. Right, so back to our memory. One important aspect from the software perspective, what you can do and help the performance is the caching control. And if you know that you will need particular data only once, there's no point in caching that. from a perspective of both the memory operations and the interconnect signaling, it's less expensive to have a so-called non-temporal copy, either the read or write operations, where it bypasses certain levels in the cache hierarchy. However, if you will realize that you will need that data at some point in time soon, right, you will generally lose a lot if you go this path. Again, that's a higher level software design question. That's a very lightweight overview into contemporary memory operations. Any questions, any comments from this side? And otherwise, we'll move into the compute component. No. All right. So if we look from a processor core perspective, and now we are talking about something that we cannot touch with our hands, that's more of a logical concept. If we are looking from a core perspective, that's an element that from one side gets fed instructions, and from the other side it touches the working data set. Let's look into more details of what's happening there. Starting from the very beginning, it needs to fetch the instructions. A very simple operation, just read the block and pass it further on for further processing, and continue and continue and continue non-stop. All is quite simple if you have a linear code block. That means that you have a sequential stream of instructions, no branching, no calls, no other diversions from the sequential execution. There might be branches. There might be branches that you don't necessarily know whether they are taken or not taken. There might be indirect branches. There might be incoming branches. That means that you will need to start fetching code from somewhere, maybe at some unknown point in time. And that's where the branching control and the mechanism that allows you to try to guess where you need to fetch the code from next is coming into play. Branch control, in fact, if we're talking about the contemporary platforms, that's first one of the most complex parts of the core. Second, that's one of mostly the dominant part that allows for the largest performance gain. It's not uncommon to see the correct prediction in the order of 90%. And that certainly helps performance-wise. Now, you don't need to expect magic here. If your working set is random, or if your branch outcome is truly random, no branch predictor will help you. It will absolutely fail statistically every second time. And, well, you cannot do anything about that. However, that's not necessarily the real-world cases unless you are dealing with low levels of cryptography and things like that. For the most of, say, common case scenarios, there's a very strong dominance whether this particular branch will be taken or not taken, and there's also a very strong correlation with the outcome of the branch prediction and the branch target. How that's implemented internally? Well, oversimplifying, that's just a set of various tables, hash tables in general, indexed by various properties. The simplest one is being whether the branch is facing forward or backwards. Backwards means taken, forward means not taken. You might have certain hints put into the code saying that this prefix means that it's taken, this one means not. You might have certain counters, meaning that if this branch has been taken 6 times previously, that means next time it will also be taken. You can have more complex structures that recognize patterns, like taken, taken, not taken, 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 not taken. That's rather easy to predict. You have just a shift register. At each iteration, you shift it by 1 bit, and then you match the pattern, and based on the outcome of that, you predict whether the next one will be taken or not taken. Then there are hierarchies of what is called attack geometry. Basically, something like a tree-based structure which looks into patterns of patterns. Again, this comes down into how much additional memory and at what cost and at what speed of a lookup you can do that. You need to memorize that branch prediction happens very early in the processing cycle, and you depend on basically you are blocked by the outcome of that. If you spend a large amount of time waiting for a branch prediction output, there's no point in doing that. It will be faster to actually execute that first speculatively and then come to the final result. Therefore, the complexity here from a hardware perspective lies in multiple dimensions. First, making that reasonably accurate. Second, making that reasonably large enough, so capacity. And the third one, making that reasonably fast. And, well, capacity and speed, generally, they are very orthogonal dimensions. Now, we already have the stream of our incoming discussion instructions. Let's move forward, decode those, and prepare for execution. The important aspect to know here is that the actual code doesn't execute instructions that you are feeding in. It executes operations. That's internal representation of what it deals with, and that's absolutely dependent on a particular implementation. x86, for example, has its own instructions, but that's a contract. You basically signal to the core what you want it to do. What will happen internally is a completely different format, and that format may change, and the rule changes from generation to generation. If we are talking about different product families, they can be completely different and nothing in common. Why is that done? So, for a very simple reason. If you want to build a fast hardware, you optimize for particular targets. And the way to do that is to actually be independent from the external signaling perspective. It's way simpler to translate the incoming instruction stream into something that is specific for this particular implementation. Right? For example, you have one product which is good at doing certain portion of functionality. You have another product which is good at doing completely separate portion of functionality. The way how to program those internally, that will result in a very different instructions being fed into the actual execution units. And therefore, what you see from the compiler output is just a contract. That's definitely not what the core internally executes from its perspective. It takes and translates that into something of the internal representation. Now, the translation might get interesting, and that's something that is quite full of various myths and misconceptions. So x86 is a variable length instruction set. That means that instructions can be anywhere between 1 and 15 octets. Technically can be longer. If you follow the encoding rules, you can go until 18, if I'm not mistaken, but anything below, anything above 15 is considered to be an illegal instruction. And there is a widespread misconception that, first, this needs to happen serially. Therefore, all these talks about out-of-order execution, multiple instructions per cycle, and things like that is not true. Second thing, that this is very complex, and as a result, this is slow. No, not at all. Let's look at a practical example. By the way, anyone can decode that? Hardware is inherently parallel. Therefore, doing many operations of exactly the same time in parallel comes absolutely cheap, and that's how the hardware, in fact, operates. Therefore, what we do, we have here, I think that's something like 20 bytes, and let's do imaginary decode of x86. We take all 18 of these octets, bytes, and compare that to a pattern. C3 is the red instruction. We compare all 18 to this particular byte pattern. We get an answer. 2 of those match. Fine, we have decoded those, right? Not so fast. Let's look at some other pattern, right? FF is increase some particular register, and then there's an immediate byte following that. What does that mean? So we made 16 or 18 comparisons with FF, 2 matches. Then we need to look into a subsequent byte. And if subsequent byte makes sense, logically matches to the requirements of the first instruction, that's a potential match. Again, well, we think that we have decoded those. Let's look a little bit further. We compare then for the BB, which is in fact B8 plus an immediate encoded in it. and it potentially matches. Now it puts a requirement that if we decode something as B8 plus, that means the following subsequent 4 bytes is an immediate here. The actual value that will be put into the register. That's fine. Let's decode another one. So we match 16 of those for 41. 41 in this particular instance is the Rex x86-64 prefix. And in total, we get this, right? All of this happens in... Was there a question at the back? No, that's fine. All of this happens in parallel. All of this happens, basically, this doesn't require containing the state. So it's just a combinational logic, right? Technically, this can happen within single clock cycle. Again, green color is happening in parallel. We match for another pattern. We have a few matches of pop the particular register. We have a prefix 41 in front of that. It modifies the actual instruction. Then we have another one. That's just a move immediate to a particular register, 8-bit register. But if that has a prefix, the meaning of that changes. That's move with 0 extension. And again, if we decode, apparently there's mod reg and indicating that there is an immediate following behind that afterwards, right? And then eventually it gets decoded into this one. So in summary, all of that technically and in many cases practically can get decoded in a single cycle in parallel and without much additional complexity. Right. Certainly, there is complexity in all of that. There are corner cases, and you also need to replicate this logic that many times as your fetch block width is. For most of the contemporary platforms, it's 16 bytes. So the platform fetches at 16 bytes at once. Therefore, this logic needs to be replicated 16 times. Is that a large cost? Absolutely not. If you look at the overall budget of logical elements that is required to implement a processing core, and that's on the level of a rounding error. Therefore, the argument that fixed instruction length ISAs like ARM, RISC-V or something have a dominant advantage that they are easier to decode, no, that's not. Again, if you look from the perspective of the actual input into the performance, decoding mostly comes to I cannot say that to a rounding error level, but that certainly can be neglected from the load that it adds up to the whole processing. Actually, dealing with caching, dealing with branch prediction, scheduling the instructions, and actually executing that is far more complex than decoding this, right? So once we have decoded that and translated into internal representation, I'll go one step back. What we have decoded here was on the contract level, on the x86 ISA level. Then this gets translated into the internal representation, different register identifications, different command sets, and so on. And that's completely machine dependent, and that's not something that, unless you have really strict NDAs with a particular processor vendor, that's not something that you will have much visibility into. And I would argue that you probably don't even need to. When all of that is decoded, it gets into various queues, waiting for most of the parameters to be available. Because we are talking about the concept of out-of-order execution. That means even if you signal something in the program order, the machine internally can execute that in some other particular order, not necessarily sequentially as it was signaled, as long as it returns or retires the instructions in the machine order. Talking a little bit now on a topic related to decoding and decoding complexity and decoding efficiency. Let's see how that relates to the actual work that needs to be done. For the x86, moving a 64-bit constant into a variable which maps into a register is really simple, right? You just have it as an immediate and you do it. For MIPS, The interesting problem here is we have a 64-bit immediate, but our code word size is 32 bits. Therefore, even if we try really hard, we cannot squeeze that into. And even 2 instructions are not enough, because you also need a few bits to indicate what you want to do with the actual immediates. Therefore, it ends up with this sequence of 6 instructions, and that's basically just logical operations. You take a fragment, you shift, rotate to do whatnot, or it with some other fragment and load it. Logically, it does exactly the same. Is that more expensive than just running one even more complex instruction? Certainly it is. Can this be optimized somehow? Yes, and we will see how. Just look. First, we take a look at some alternative realities. RISC-V, exactly the same thing with just a few bits shuffled around. Spark, pretty similar, different encodings and slightly different ways of how you signal the arguments there. ARM. ARM, well, learned a few lessons and made things a little bit more optimal, recognizing that this is a really common instruction pattern. But still, for the cost of one logical operation, we need to signal four actual physical smaller level operations. What can we do about that? There's a notion of fusion. The decoder stage may detect this as a pattern and internally decode this into as one or not necessarily 4 logical operations. That's precisely why it's called fusion. It glues multiple instructions or multiple signaling elements from ISA perspective into a less number of the internal representations. This is indeed complex. You cannot be certain whether the compiler will emit it in this particular order, or it will swap, for example, instructions number 2 and number 3 here, and that pattern detection might break or might not, depending on how much complexity you put in there. Right? But from a practical point of view, this looks reasonably unneeded. Basically, to an extent, that's a level of complexity that you have to have because of your instruction set restrictions. You cannot have more than like 20 or 22 bits of useful immediate payload if your whole code word size is just 32 bits. Then, once everything is decoded and ready there, we are moving into the actual out-of-order execution. From an ISA perspective, you have a set of registers, and many software engineers dealing with the low-level things generally complain that you always have too few, and I would tend to agree. However, inside of the machine, you have multiple tens or sometimes hundreds times more of registers available. You cannot easily access those from a software perspective. The register that you signal from ISA perspective is just a contract saying that, well, logically, this register binds to some other registers outside of the instruction. However, you don't need precisely to follow that. As long as the actual execution logic stays the same, you can easily replicate those internally. And if you signal this particular register in this instruction and in the subsequent instruction, they don't necessarily need to match, and generally they don't. That means that there will be multiple names for different physical registers, all at the same time active within the machine. And this is basically a data flow type of processing architecture where you have your instructions be waiting until the data that they need to process on becomes ready. Once that is ready, that goes into the scheduling. Because not all instructions take the same amount of time to execute. Not all of the instructions require equivalent amount of internal resources. That's basically a resource planning question. And finally, we come into the actual execution. So you can add or shift or do some more complex things here. The feedback of the execution goes back into the branching unit. So that's precisely where the branches are confirmed. So prior to that, we were fetching the code, I cannot say blindly, but speculatively, thinking that we will get onto the right branch, and all the decodes and all sorts of other activities were happened tentatively. Therefore, we are doing the work with, to an extent, to a credit, saying that most probably that will be the right choice that we have made, and therefore we will save a little bit of time. Execution phase confirms that. That's where the logical expressions get evaluated, and you actually see whether you have taken the right branch or the wrong one. And on the right, you can see the load store queue. That's the interface of the execution system into the memory. It's not yet the cache. It's something that keeps the tentative memory operations that can be rolled back. Keep in mind that as we are talking about a speculative execution here, if we read or write to memory, that does not necessarily mean that it needs to be visible. Therefore, the memory operations are also kept in, say, controllable restriction, and only afterwards, when the instruction is confirmed that there are no exceptions, that everything else is fine, it gets signaled into the cache hierarchy, and then from now on it starts to be visible to other cores. And there's a memory hierarchy, and eventually we reach out on the right side to the memory component that we have been talking in the beginning. Now, what's out of order of all of this? And not in the sense that it is broken, but when you hear the notion that this particular core is out of order, what gets executed out of order is really a small part. It's actual execution of instructions. Everything else is in order. That means that the decoding, the dependency checks, the derivation of which instructions can go one after the other and so on, that's all done in the program order. And again, the retirement is also done in the program order. However, what's done speculatively? Pretty much everything, right? All of what we have been discussing here is kind of done virtually. As we are not certain whether our branches are correctly taken, we just, well, we take a guess, and we run as if that was the right choice. If we happen to make a wrong decision, and we'll come to the examples in a moment, we have to flush everything that we have did. That means we just throw away a big portion of the work, and we restart from the point of where we took the wrong decision. About addressing. From a software perspective, on the left side of this, you are dealing with the logical or virtual addresses. Then, starting from a cache hierarchy, it gets translated into the physical, and that's how the rest of the system and the memory interface deals with that. Now, enough of the theory. Let's look at some practical examples. So let's look at how the branch control works. By the way, any questions, any comments? Anyone online having anything to comment? No? That's fine. Right, so here we have a very important function doing something depending on the condition, right? It's just for illustratory purposes, right? It compiles into what you can see on the left. The actual code is on the right, and let's see how that works with the argument of 42. We fetch a cache line, we decode, throw away what we don't need. This is an example of the 4-wide decode machine, which can decode 4 instructions per cycle. All right, this gets decoded into this sequence of code, and the second one is conditional, but as we don't have any history for that, well, the only thing that we can make the decision is based on a direction. It's looking forward, and the convention on x86 that forward branches are not taken. That's one of the reasons why, if you look at the error handling code, the compiler generally tends to put error handling blocks at the end of the function, and all the jumps into that are forward. Therefore, they are not taken. Right, so fetch another block. That's an unaligned fetch. Memory system works best when that is aligned on some boundary. In our particular case, that's 16 bytes. So this is a more expensive fetch, probably twice as much. We fetch another block. We decode that. right? Throw away what is not needed. Then in this block, we see an unconditional branch. Unconditional branch means that we will have to follow that. Therefore, what we decoded beyond that, we need to throw it away. It's useless for us. We go to that point, fetch again, unaligned, decode, and send it out to execution. And what happens? We actually execute the wrong branch. Is that a problem? No, that's not a problem at all. The machine eventually coming to the execution will notice that we have executed the wrong branch because the actual comparison result will be available only at the execute stage. Throw everything away, come back, basically roll back to the point of the first wrongly predicted branch, redo the same example that we had here, and then execute the green part. All fine. Works logically correctly in any case, just that the cost of doing this is precisely twice in this example. Now, let's repeat our example with a different argument. So given that now our branch predictor is trained, we run exactly the same code, do the same story, fetch, decode. History is now present, saying that, okay, now I know how to deal with this branch, so I fetch from there, feed that again, repeat, and then once we execute that, we realize that the branch was incorrectly predicted. Exactly the same thing, throw everything away, refetch and redo. One of the more important new developments in contemporary platforms is a two-way decoding or multi-way decoding, even more than two. In case when there is a conditional branch, the machine can fetch from two locations at once. So basically, fetch from here, fetch from a target, decode, feed, and you will, with a high probability, you will have at least a portion of the work that will eventually be done already flowing in your pipeline. And in case of the branch misprediction, you don't need to restart from the decoding phase. Right? So that's pretty much what is happening. You are starting to fetch from the branch target, and you feed those instructions into the decoder. However, what the smart compiler did, and this is actual code, it actually initially made both of the branches to be executed, and that's what is signaled. And only the result of one of the branch, depending on the actual branch outcome, is taken. So you cannot tell without a broader context whether that's a benefit or a loss. From a micro benchmarking perspective, you can certainly come to some outputs, but micro benchmarks may be very misleading. And if I would have to give you one recommendation about dealing with all these low-level things, don't believe your micro benchmarks. They are fun to play with, but generally they don't show the right context. Right? Certainly, if your application is doing just that, what we have here all the time, you will care about micro benchmarks. But the overall performance gain from these low-level optimization, it comes as a summary of all of these small items spread around the large portion of the code base. Let's look at some other examples. Memory copy. That's something that happens mostly all the time, and it certainly would be better that it performs reasonably well. What's the complexity with that? Not always you know, and not always you can control the alignment. Alignment of both the source destination and also a relative alignment source to the destination. You certainly can try and do smart things like detecting the platform, detecting the layout, alignment, many other things, and then actually do the copying. What if you could try and offload this to the actual hardware platform? So one thing is various types of accelerators that we're seeing more and more into contemporary platforms, but generally those are heavier, for heavier tasks. If you are dealing, for example, with network packets or things like that, where it's on the order of 1,000+ bytes, certainly accelerators and the overhead for specialized accelerators might be justified. If we are dealing with copying on the order of tens or hundreds of bytes, which is the majority of memory cases, that's an overkill. So let's look at how that could be done. We take a simple naive case, scalar, unvectorized memory copy. It compiles into something like that. The compiler was gently told not to do two smart things here. This is for illustratory purposes. Memory caching system might help you here, but this is way suboptimal. If we allow for some more creativity for the compiler, basically auto-vectorization, then the result will be slightly better at a kind of higher instruction footprint. If you look into handcrafted memcopy, and that's quite a lot, this is actually taken from a ClickHouse project. This compiles into something like this, and again, compiler changes quite many things behind the scenes. Certainly, it works from a functional point of view. However, you still cannot be certain about the relative alignment of a source and destination, and in general alignment into the memory and other platform restrictions. What if you gently ask your underlying platform, please copy this block from this to that, that many bytes. Thank you so much. And this is where we are coming to the domain of why certain implementations of certain compute platforms are fast. Yes, it's x86. It's enhanced rep move, enhanced rep moves instructions. Basically, the core itself can recognize this particular instruction and interprets its arguments as basically parameters to an internal subroutine, a microcoded sequence of instructions that, depending on the alignment, and the core itself can check the alignment, can check the size, and choose the right stream of internal operations that can be fed into the execution. From a user space signaling perspective, that's just one instruction. However, into what it maps internally, first thing, is completely platform dependent and invisible. Second thing, that's how you actually gain the performance. ERMS is a right thing to do on the platforms that support it. And that's just one of the examples. Plenty of such micro acceleration type of things are getting more and more into contemporary platforms, like specific cryptography acceleration. That's mostly how you gain performance on contemporary platforms. It's not that x86 is fast. It's a particular implementation of x86 is fast. It's not that ARM is fast. It's a particular implementation of ARM. This specific instruction set level is fast. And it's about all these internal kind of implementation details, which are only signaled via external ISA. Another example about the hashing and why algorithms matter. So here we have a Fowler-Nolvo hash function, a really simple thing which just does some multiplication and exclusive OR. It's very widely used. Pretty much any standard runtime library uses that for the hash table implementations, hash maps. Right? And that's to what it compiles. Here we see an example of where the fusion can happen. So basically, decoder will see a pattern of those two instructions and emit one internal operation for that. Then what gets fed into the execution units is a sequence. Basically, the hardware will unroll the loop itself. And it will most likely run out of bounds. And that's absolutely fine, and we will see why. That's what gets fed into the actual execution units. Right? Then each iteration gets a new register allocated. That's the internal physical register. That means that all of those instructions potentially can run in parallel and potentially out of order, and they in fact will run out of order. Memory operations will happen on its own. Once we get a result from a memory operations, then we'll do the logic. And even, for example, here, if we run that hash function on an object that is like 3 bytes here in this example, the hardware will happily run for subsequent elements, because everything that we're executing speculatively. The first instruction that gets either an exception or finally the branch is confirmed that it is wrongly taken. From that point on, exception either will get signaled or it will be silenced depending on the instruction, or if the branch is incorrectly taken, everything will be flushed, and then the execution will follow from the override place. Here's an example of a slightly more complex hashing. You have a composite key. So basically you have 3 key elements that all need to be hashed subsequently. And what's the logical cost of that? So here we have in separate translate units that will be a call. First one probably will be mispredicted. Subsequent ones will be correctly predicted. Not a big deal. And at the actual callee site over here, you see that we will again run speculatively a loop. If we can inline the things, that will be merged into one. Again, the important point here is that speculation will stop, speculation will not be able to bypass the first branch. Therefore, it will happily run multiple instances of the first loop, but it will not touch the second and the third hash loop here. Once the incorrect branching is confirmed for the first loop, it will start running on the second one and happily will run out of bounds until the incorrect branch is predicted, confirmed, and then the third loop will be started. If you actually do a logical change here and from a code perspective use it in a different way, basically combine the length of all the keys and treat that just an opaque object, you will have one loop that eventually gets mispredicted. So, a few words about why all of this matters and why are we talking about this. Nanoseconds do matter, nanoseconds do add up, right? All these small things might shave you a few cycles or a few nanoseconds. And eventually, the difference in performance, once everything is sorted on algorithm level, once everything is sorted on a data structure alignment level and actual data structure choice level, the performance comes down to micro optimizations. Please don't do it the other way around. Starting with the micro optimization is certainly fun, but very often that will lead to well, just practically irrelevant results. Now, the important task here is first to understand what the bottleneck is, and that's about performance measurement. That by itself is a very platform-specific and quite complex area in a sense that the deeper you go, the more divergence is even within the same family of the same vendor products. We cannot talk about uniform performance management interfaces or approaches between different processor architectures like x86 and ARM. They do things in a completely different way. You can abstract that on a certain higher level, but the higher you go, the more you lose of those tiny details that you eventually will really want to see that. Going deeper, say from one generation to other generation, the differences in performance management infrastructure might be very different and absolutely incompatible. Is that a problem? That's just a reality, right? The fact of life that if you're dealing on this level, you certainly need to look into very specific details and be ready to change that as your platform changes. The practically important part about the micro optimizations, you need to choose one area and sort it out first before moving to other areas. Once you start dealing with multiple dimensions, this gets into geometrical progression, and at the end you get noise. Certainly not an easy topic. However, if we are looking on a broader scale, say fleet-wide optimizations, that's certainly worth the effort. You can easily talk about gains of thousands of percent, so basically orders of magnitudes, if you pinpoint the actual bottlenecks in the right way. And in general, well, maybe looking back from my own experience, the hardest part is trying to understand where the bottleneck is and why it is there. Once you understand that, fixing that often is just a trivial thing. However, coming to the bottleneck is fun and way harder. Now, a few more on a philosophical level talks. So we have been talking here about the instruction sets and signaling to the machine, why the machine internally does something on its own, mostly negating all of what we did. If we try to compare the three dominant general purpose architectures today, that's x86, RISC-V in its own various implementations, and ARM in its various implementations. And if we try to match those, we certainly see a lot of commonality. Mostly the same number of registers. Don't be surprised, x86 is getting 32 registers pretty soon. The others already have that. Well, it's 32 in theory, it's less than that. Even today we have not 16, but 14. Somebody might argue that we even have 8 only, right? Those are probably the details. Other architectures have their own restricted use registers too. The main difference probably revolves into whether the machine is a load store architecture where you don't have to deal with memory operands directly, or whether that's a register memory machine, which x86 is a dominant part. That's the amount of the goodput that you need, that you can gain out of your ISA. Remembering our examples about constants, load store machine generally will lose to the regmem machine for these types of tasks. And if we are looking from a practical code perspective, that's what constitutes a dominant part of the loads. Yes, there's a question at the back, so please wait for the microphone.
Are there tasks for which the load store machine is superior then?
Yes, generally logic. If you have a large amount of logic that you load data once and you only process that, like cryptography, for example, if you have a round of cryptography block, you load the data once, then you run a large amount of logical operations that deals only within the registers, and then you just store the things out. However, exactly the same you can do with regmem machine.
Oh, not really.
Not really, and that
Okay,
is one of the arguments that is, again, is a myth or a misconception in the field, saying that we have a machine that has simple to decode instructions, that means fixed width. Well, we have seen what's the benefit out of that, which are fast to execute. We have seen what it takes to execute an instruction, and they operate only on the registers, and registers are fast, therefore everything is fast. Well, you probably have seen yourself that if you want to build a fast platform, you actually need to build fast components out of which you build that platform. Basically, the internal implementation details and not the external ISA-facing things. So to summarize to your question, this is much more of a philosophical debate than the practical difference. Right, so we have one third part here in this presentation about vectorization, but I do see that we are running short of time. Therefore, probably we will have to leave this, and if you are interested, we can chat over here, and you will see that in the slides. The only part that I will show here is about the relative ordering of vectorized, accelerated, and scalar operations, and what benefits you can potentially gain here. So this is x86 and SHA-2 instructions for x86. So SHA-2 is a cryptographical hash function which takes a large amount of bits, shuffles it around, and spits it out. If you take the scalar implementation as a reference, if you use the specific accelerated instructions, that's 4 times gain latency-wise. So basically, it runs 4 times faster. If you vectorize the thing, you will lose on the latency side because the vectorization has its own cost and there are some inherent complexities related to the algorithm. However, throughput-wise, you easily outperform the accelerated one. And that's basically the summarization of why vectorization is generally the right thing to do. You decode the instruction once. From a logical perspective, generally you will lose a little bit on the latency, but on the throughput, you will gain in ideal cases, you will gain the ratio of your vector register length versus the processing element length, right? So AVX 512, it's not uncommon to see speed up coming to 16 times. It certainly can be achieved. And again, the important part, that works only if your data structures allow. Right, we are 1 minute out of time. And with this, I will open the discussion. Right. So, any questions, comments, feedback, gifts, bribes? Yes. There's a question in the middle. No, it's over there in the middle.
Okay. My question is for your first hashing example. So you mentioned that everything works on different registers, the logical ones, to allow speculative execution.
Yes.
But there are still dependencies between each steps, because each step still depends on the previous one.
Are you talking about basically the hash functional loop unrolling one, right?
Yeah, the first one, yeah.
As long as there is no data dependency, and there is no data dependency here, you can see that we are working on subsequent bytes. There is no dependency between the registers. The important thing here, right, if you see, for example, over here, like this EDX, and this EDX, they have nothing in common. That's just a signaling, right? Internally within the machine, those are different registers, and that's what happens inside, right? So it allocates 100, 101, 102, right? Those are just, well, imaginary names for that. But from ISA perspective, that's only a contract. What happens inside, if the machine can prove that there is no data dependency, and in that particular case, there is no data dependency because the address is clearly different here, and we are increasing it here, right? So it can certainly run ahead and do those in as much parallel as possible.
Thank you.
There are 2 questions there.
Yeah, maybe can you recommend a specific profiler if you're not bound to a specific architecture that points out these issues?
Apologies, if you could repeat the first part.
Can you recommend some profilers?
Profile tools, basically.
Yeah, profiling tools, like VTunes, for example, that cover multiple architectures, or is this not available?
All right, so VTune itself is more of the user interface and analysis thing. Certainly it can capture, right? But the important part here is basically getting to know what kind of counters to capture, processing that later. So VTune generally is a good all-purpose tool which doesn't go that deep, right? But again, I would argue that for many of your day-to-day cases, that will be more than enough. Only if you are dealing with custom hardware platforms, you would need to look deeper. Another important and reasonably good tool is MCA, the microarchitecture analyzer from LLVM. However, that tool is as good as the platform definition file is. right? Therefore, sometimes you really need to be critical of how it treats the platform and its capabilities, and sometimes that requires fixing, especially if we are talking about the newer platforms. Now, about collecting the actual performance counters, generally there is no one answer, because that's something that has to be integrated very deeply into your code base, because it has very, say, externally visible collateral damage. Right? The cost of collecting the performance counters sometimes is way higher than the actual block that you are trying to measure. Therefore, this needs to be taken with a large amount of consideration. But overall, MCA and VTune and, well, there's Osaka, there are some other code profiler analyzers, reasonably good tools overall. Yeah. There was another question at the back.
Last question.
Is there a major difference between branch prediction algorithm on different architecture?
Generally, so implementation-wise, yes, very, very big differences as such. Now, majority of that is not public information at all, and therefore, I would say, it doesn't matter that much to the external field. From a performance perspective, is there a big difference between 86 and 87.5% accuracy? For some tasks, it's a lot. For some others, well, it's just a rounding error, right? Therefore, I don't believe that there is one answer to your question. Yes, the algorithms are different, and generally different vendors do things in a similar direction, but very differently internally. The overall outcome of that, it's good enough for majority of the practical cases. Only in the very specific cases, those differences become critical. But certainly such cases do exist. All right, colleagues, we're out of time. So thanks a lot for all of you here.